Now let's look at telescopes since the time of Galileo. How have telescopes changed since Galileo's time? And how do they help us to learn about the universe? There's a straight path from the small telescope that Galileo used, which you could replicate today for $5 or $6 worth of components, and the behemoths that now sit around the Earth's surface collecting light from the distant universe. They're essentially the same type of object. Telescopes collect vastly more flux than our eyes can do, so their light collecting area is one main property. They can also see much more detail than our eyes, so angular resolution is their second major property. We also now have telescopes or instruments that can detect radiation that's invisible to our eyes. That was not possible in Galileo's time. For example, infrared and ultraviolet. And if we go into orbit above the Earth, we can detect even shorter and even longer wavelengths, like gamma rays and X-rays. In general, with telescopes, bigger is better. More light collected, and the images are sharper, but they're still subject to the limitation imposed by the atmosphere. Here's a diagram of how telescopes have progressed in the last half century. And you can see that there was a logjam where the Palomar 5-meter telescope was the largest optical reflector for some 30 years, until a large new set of telescopes started to be built in the 1990s. On the left, we see ground-based telescopes, which now have gone to 10 meters with the Keck telescopes and are heading towards 20 and 30 meters with the GMT at the bottom and the CELT. On the right are the largest telescopes in space. Space is expensive, probably costs 10 times per square meter of glass to get into orbit than it does to operate on the ground. And the largest telescope there is going to be the James Webb Space Telescope, 6.5 meters. Here's a graph of optical telescope size versus time, and it actually shows, with Galileo's data point there, around 1610, that on a logarithmic scale, telescope size or aperture has actually grown exponentially for 4 centuries, which is remarkable, especially given all the various social, economic, and technical factors that go into building a telescope, a piece of hardware, technology. If we were to extrapolate from the Keck 10-meter telescope, which was built in the early 1990s, even at this rate of growth, we would predict that it would be a very long time, over half a century, before we could have a 50-meter telescope. And so in a sense, it looks like we're hitting some natural limitations again. The largest telescopes that are being conceived of are 20 and 30 meters. And indeed, to go to 50 or 100 meters, it's not clear how we would do that. But this is a glorious time for the construction of large telescopes, as we'll see. Angular resolution is the minimum angular separation that a telescope can distinguish. In other words, how close in angle two objects appear to be on the sky. For the naked eye, this is about 1 minute of arc, 1/60th of a degree. Remember, the full moon and the sun diameter is 30 arc minutes, or half a degree. So it's 30 times smaller than that. The normal limit due to turbulence in the atmosphere is 60 or 70 times smaller, so about 1 arc second or a little less than that. Telescope resolution is improved with a larger mirror. You can see the formula for the minimum resolution or minimum angle resolvable by a telescope. So small angle is better here. And you can see it goes inversely with the diameter. So bigger telescope gives a smaller angle that can be resolved, and it goes with wavelength. So longer wavelength gives larger angle that can be resolved. In other words, the best images are made at short wavelengths and with big telescopes. And the images on the left show how resolution affects observing a double star, where when the resolution is poor, the images are just blurred hopelessly together, and you wouldn't even know there are 2 stars. And when the resolution is good, you can clearly see that there are 2 stars. There are 2 basic telescope designs. The refracting telescopes, which is the kind that Galileo made and used, using lenses, and they're limited by various things such as chromatic aberration, which we've discussed, and also mechanical sagging and flexure, because as the telescope lenses get larger, the tube gets larger, and it becomes a large, heavy object that will flex under its own weight and as it moves around the sky, and that, of course, will affect the image quality. The second major telescope, not invented until Newton's time, is a reflecting telescope that uses mirrors, and almost all research telescopes today use reflecting designs. The largest refracting telescopes have not been doing research for about a century. And that's the end of this topic.